today we are going to talk. Today we are going to talk about process scheduling, which is part of operating system subject. So here we discuss about why we need scheduling. So first we discuss what is scheduling. So process scheduling is an essential part of a multi-programming operating system. So what is multi-programming operating system? Multi-programming operating system is a system in which more than one process are loaded into the executable memory at a time, and the loaded process shares the CPU using time multiplexing. A typical process involves both input-output time and CPU time. So here in uni-programming system like MS-DOS, time spent waiting for I/O is wasted and CPU is free during this time. In multi-programming systems, one process can use CPU while another is waiting for I/O. This is possible only with process scheduling. Go to next slide. So here we will see CPU I/O burst cycle. So process execution begins with a CPU burst. CPU burst means when a process gets a CPU first time. This is followed by an I/O burst, which is followed by another CPU burst, then another I/O burst, and so on. Eventually, the final CPU burst ends with a system requires to terminate execution. So here we can see there is two types of program. One is I/O bound program and second is CPU bound program. So in picture A, if you see, there is long CPU burst, and after that there is a short I/O burst. Here you can see long CPU burst, short I/O burst. After that again a long CPU burst, then a short I/O burst, then again after that further. But in picture B, if you see, there is CPU burst is very short, but I/O burst is very big. So again short CPU burst and very big I/O burst. So these two process. So an I/O bound program typically has many short CPU burst, and a CPU burst program might have a few longer CPU burst. So a program which has more I/O needed, this is called I/O bound program, and a program or process which is more CPU needed is called CPU bound program. So here you can see first there is CPU burst, there is I/O burst, again CPU burst, I/O burst, and so on further. So here first you have to load in a store, add to a store, read from file, then again wait for I/O, and then further you can execute your process. So go to next slide. So here we discuss about CPU scheduler. So the short-term scheduler or CPU scheduler selects a process from the processes, means more than one process is there, so we have to select one. So here if you see, we have to select one process and give this process to the CPU. So here you have to see queued processes and scheduler select some, and after that dispatcher give one process to CPU. So one CPU at a time can take one process and other process can wait. In this figure which is below, you can also see there is a new job which is comes to input queue. After that admission scheduler takes 3 or 4 or some process to main memory, and after that one process goes to CPU. Next slide here you can see. So now we will talk about preemptive scheduling. So CPU scheduling decision may take place under the following 4 circumstances: when a process switches from the running state to the waiting state, for example as a result of an I/O request or an invocation or a wait for the termination of a child process. Second is when a process switches from running state to the ready state. So for this example, when an interruption occurs. Third is when a process switches from waiting state to the ready state, for example, at completion of IO. And fourth is when a process finally terminates. For condition 1 and 4, there is no choice. A new process must be selected because in case 1, if you see IO request is there, so we have to choose one more process. And in case 4, if you see process is terminated, so anyway we have to choose next process. But in condition 2 and 3, there is a choice to either continue running the current process or select a different one or next process. If scheduling takes place only under condition 1 and 4, then the system is said to be non-preemptive or cooperative. Under these conditions, once a process starts running, it's keep running until it either voluntarily blocks or until it finishes. Otherwise, the system is said to be preemptive. So basically, I am trying to say that in non-preemptive process, when a process comes to CPU, then it will uh, execute further its completion till its completion, and after termination another process or next process can come. But in preemptive process, where we can use more than one process. When a process go for IO works, then we can give second process a chance to use CPU. So this is a difference between preemptive process and non-preemptive process. We can stop a preemptive process, but we cannot stop a non-preemptive process in middle. In a non-preemptive process can run from start till its termination. Here we will see dispatcher. The dispatcher is the module that gives control of the CPU to the processes selected by the scheduler. This function involves context switching, switching to user mode, jumping to the proper location in the newly loaded program. The dispatcher needs to be as fast as possible as it is run on every context switch. So what is here we'll discuss what is dispatch latency. So dispatch latency is the amount of time required for the scheduler to stop one process and start another process. So in preemptive program, we have to stop one process and start another. So in this case, we can use the dispatcher. So here you can see these are some states. So first we have to create a process. After creation, we can go to ready state. From ready state, by using dispatcher, we can go to running state and till go to termination. But from running state, there is also a possibility then a process can go to blocking state, or after a timeout we can go to ready state. And from block state, again after IO operation or some other things, a process can come further back to ready state and run till its completion or termination. So now we'll discuss about scheduling criteria. So different CPU scheduling algorithm have different properties, and the choice of a particular algorithm may favor one class of processes over another. Which characteristics are used for comparison can make a substantial difference in which algorithm is judged to be best. So in this picture, if you see, there is a process when interrupt the processing process made available at this point. After process made available, then what happens? There is conflict, there is context switching, dispatch. Then after finally a process gets to CPU, which is called real-time process execution. But here if you see, from event to response to event, this total time is called response interval. So here if we add all these times, then this will becomes our response interval for a process. Here there are several criteria to consider when trying to select the best scheduling algorithm for a particular situation and environment, including, so there is first thing is what CPU utilization. So ideally the CPU would be busy 100% of the time, so as to waste zero CPU cycles, means we are working at our maximum efficiency. On a real system, CPU usage should range from 40%. 40% means lightly loaded to 90%. 90% means heavily loaded. So here we'll talk about throughput. So what is throughput? Number of processes completed per unit time means in 1 unit time how many process we are completed. So on an average we calculate throughput. So may this be range from 10 process per second on 1 hour depending on the specific processes. Now we'll discuss turnaround time. Time required for a particular process to complete from submission time to completion. This is also called wall clock time, time which we just calculate generally. So this is called turnaround time, means total time taken by a process to complete, in which we also add there IO time, waiting time and actual CPU time. Waiting time. Waiting time is the sum of the time processes spends in the ready queue waiting their turn to get on the CPU. Next is response time. Amount of time it takes from when a request was submitted until the first response is produced. Remember, it is a time till the first response and not the completion of process execution finally. So, what is response time is amount of time taken by a process when it firstly gets the use of CPU, means first time when a process get the CPU is called response time for the process. Go to next slide. In general, we want to optimize the average value of the criteria, like we want to up our CPU utilization and throughput to be maximized, and we want to minimize all other criteria like turnaround time, waiting time and response time we want to decrease, and we want to increase our CPU utilization and throughput when we have to select any CPU scheduling algorithm. But sometimes what happened, it is most desirable to minimize the variance of a criteria than the actual value. That is, a user wants a consistent, predictable system than an inconsistent one, even if it is a little bit slower. So it depends upon choice of user, that according to user choice, a user can select type of CPU scheduling. Which algorithm suits him, a user can choose. Now we will discuss about scheduling algorithm. So our first CPU scheduling algorithm is first come first serve scheduling algorithm. The first come first serve FCFS is the simplest scheduling algorithm. The process that requests the CPU first is allocated the CPU first. So simple. Which process comes first, then we will get the CPU first. So this is called FCFS algorithm or FCFS scheduling algorithm. The implementation of FCFS policy is easily managed with a FIFO queue. FIFO queue means first in, first out queue. When a process enters the ready queue, its PCB is linked into the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. So means PCB is process control block. So its PCB is linked into the tail of the queue, but after that when the CPU is free, then we can allocate the process the head of the queue, means the process which is present at the first point at the queue. The running process is then removed from the queue. The running process then removed from the queue. On the negative side, the average waiting time under the FCFS policy is often quite low. We will see this in our next slide, that why waiting time under the FCFS policy is often quite low. So here by this picture you can understand what is first come first serve. Here you can see there is process 1, which gets CPU, and there is a longer queue, process queue. So but if process 1 go for IO operation, but we cannot give CPU to process 2 and 3 or 4 because these are These are non-preemptive algorithm, and we cannot stop them in middle. We cannot stop them in the middle, and they can execute till its completion, and after termination we can add another process and give it to the CPU. So that's why this is a main problem with the FCFS, that we have a longer process queue. Go to next slide. So here we will take one more example, one example of FCFS to understand it better. So in this case we have four processes: P0, P1, P2 and P3, and their arrival time is 0, 1, 2 and 3, and their execute time means time which is needed to execute by the CPU, means they need 5 seconds to use CPU. Process P1 need 3 seconds, process P2 needs 8 seconds, and process P3 needs 6 seconds. So here we just draw a Gantt chart for this process. So here you can see P0, P1, P2, P3. So in this case we have just assumed that this process not gone for IO operation, and there is no ready queue like that. We just take an ideal condition. So we will start with first a basic and simple example to understand how FCFS algorithm works and how we can calculate average waiting time for FCFS algorithm. So here we have to calculate wait times of which each the process is as follows. So first we can see process P0 is a request at 0 seconds, and he will get at 0 seconds. For waiting time for P1 is 0. But when you see P1 is a arrival time for P1 is 1 second, but he will get first time CPU at 5 seconds. So to calculate waiting time for P1, we just subtract 5 minus 1. So we will get 4 second. 4 second is waiting time for process 2. And so further for process 2, if you see arrival time of process 2 is 2 seconds, and completion time of process 2 is 60 seconds. The completion time of process 2 at 16 seconds. So when we divide 8 and minus 2, so he comes at 2 seconds and he will get at 8. So 8 minus 2, so we will get 6 seconds at its waiting time. So for process 2, if you see arrival time of process 3 is 3 seconds, and first time he will get CPU at 16 seconds. So when you have to calculate waiting time of process 3, then we just simply first time 16, and we have to subtract minus 3. So we will get 13 seconds as waiting time of process 3. So when we have to calculate average waiting time, we just add then 0 plus 4 plus 16 plus 0 plus 4 plus 6 plus 13 is 13, and divided them by 4. So we will get our average waiting time as 5.74. We will go to next slide. So here we can see consider these three processes. So in this case, if you see there is three processes P1, P2, P3 with burst time 24, 3 and 3. So in this case, this is a simple example. So in this case, if you see, first P1 will be executed till 0 seconds to 24 seconds, and at 24 seconds P2 will get chance to execute and execute till 3 more seconds till 27 seconds, and after that P3 execute for more 3 seconds because their burst time is 3 seconds. So till 30 seconds P3 will execute from 27 to 30 seconds. So in this case, if we calculate their waiting time, so we have to, waiting time is 0 for P1, obviously we know. For waiting time for P2 is we have to, first we will get to 24, and their arrival time is 0. We assumed arrival time of P1, P2, P3 and P1, P2 and P3 is 0, and they come at the same time. So 24 minus 0, 24 is waiting time for P2, and for P3 27 minus 0. So 27 seconds is waiting time of P3. So when you add them and divided by 3, you will get 17 seconds or 17 milliseconds average waiting time for these three processes. But in second case, if you see, we can just change the order of their execution. Means we first execute P2, then we execute P3, then we execute P1, and burst time, arrival time all are same in this case. Now we have to calculate their average waiting time. So in this case, obviously 0 for P2, but for P3 this is 3, and for P3 this is 6. So in this case, we will get average waiting time is 3 milliseconds. So this there we can see in first case we will get 17, and in second case we will see 3. So here we can see there is a very much decrease in the average waiting time. So this is a problem with FCFS. If we change the execution of processes, then we'll get different kind of average waiting time. So policy is generally not minimal and may be very substantially if the process CPU burst time vary greatly. So in the problem with FCFS is that if you get a process with a very big burst time, then what happens, the